When you ask ChatGPT to draft an email, Claude to analyze a spreadsheet, or Gemini to brainstorm ideas, you are seeing the results of a specific method for processing information. Despite their different interfaces, every one of these AI models relies on the exact same underlying architecture. That foundation was established by a team of Google researchers in a June 2017 paper titled "Attention is All You Need." Before this research was published, the field of AI was struggling to manage long-range dependencies in text. Machine learning models were effective at short tasks, but failed to maintain coherence over long distances. The release of this paper changed the trajectory of the entire industry. It introduced a new architectural framework called the transformer, which provided the structural blueprint that allowed machine learning to finally scale to its current level. This diagram illustrates how AI processed language prior to 2017. These models, known as Recurrent Neural Networks, or RNNs, read text sequentially. They move like a slow train along a track, processing one word node at a time, from start to finish. Because the system processes one step at a time, it faces a mathematical issue called the vanishing gradient problem. By the time the AI reaches the end of a long paragraph, the context from the beginning has often faded away. It is like trying to bake a cake using a 15-step recipe, but being forced to read the entire list from step 1 every time you want to verify the current instruction. When we superimpose that sequential track over a modern GPU architecture, which is designed like a multi-lane highway, the limitation becomes physical. Because the RNN must finish step 1 before starting step 2, it can only use a single lane of processing power, leaving the rest of the hardware's capacity completely idle. This sequential requirement made training advanced models slow and expensive. Machine learning was trapped in a state where it could not utilize the full scale of modern computing hardware. Researchers proposed a radical approach. Stop treating sentences like a linear track. Instead, the transformer looks at every word simultaneously. To process a single word, self-attention checks every other word instantly. Varying connection lines reveal which words provide relevant context. To manage this mathematically, the paper introduced a system of 3 parts: the query, the key, and the value, known as QKV. We can visualize this using a classroom. A word-seeking context broadcasts a query, like a student asking for the definition of a specific pronoun. Another word holds the key, signaling that it has the relevant information. When the query and key match, the value, the actual meaning, is shared across the entire network. By matching queries to keys across the whole text instantly, the AI builds a map of relationships between all words at once, removing the need to wait for a sequence to finish. Understanding human language requires looking at several different types of context at the same time. To do this, the transformer uses multi-head attention. Multiple attention heads analyze grammar, theme, and relationship simultaneously. But analyzing everything at once destroys chronological order, leaving an unorganized word pile. To fix this, positional encoding attaches sine wave timestamps to every word, instantly snapping them back into a rigid sequence. This combination allowed the transformer to analyze massive amounts of data in parallel while maintaining the specific structural order required for language. Once the sequential bottleneck was removed, data began to flow differently. Information could finally be routed through hundreds of parallel processing lanes at the same time. This architectural shift allowed researchers to fully utilize large-scale GPU clusters. They could finally feed vast amounts of internet data into models without the hardware sitting idle. This led to the discovery of scaling laws. The researchers found that as long as they increased the amount of data and the amount of compute power, the transformer model would reliably become more capable. The 2017 paper provided a way for software to finally match the capabilities of modern hardware. By aligning the algorithm with the way chips actually process data, the industry could finally build models at a global scale. This synergy between hardware and software led to the rise of foundation models. The acronym GPT itself, Generative Pre-trained Transformer, is a direct reference to the architecture introduced in that original paper. By training these transformers to predict the next word across billions of pages of text, researchers created models capable of human-like reasoning and conversation. Today, the use of attention has expanded.
It is no longer just for text. It is used to analyze images, to process audio, and even map proteins in biology. Attention is all you need demonstrated a consistent way to process information. It showed that with a parallel architecture and a mechanism for weighing context, a neural network can learn to find patterns in almost any complex dataset.